Welcome friends to the 10th lecture on system reliability. This is an online course on risk and reliability of offshore structures. We are talking about lectures on module 2. We are focusing on structural reliability and reliability theory in general. This is lecture 10, where we will continue with the discussions on system reliability that is continued from the last lecture. So far we have been discussing about different methods of reliability, different levels of reliability analysis which can be applied to component level reliability analysis. So, all methods like for example, first order second moment method, advanced first order second moment method, Hasofer-Lind method, response method using linear functions for performance theorems, etc. All these are applicable to component level reliability. Let us extend the discussions on structural level. Performance of a structural component or an element is quantified as single, continuous or differential limit state function. So, when you talk about the performance function, of a structural component, what we can say as an element level can be quantified in three ways, maybe as a single limit state function, maybe a continuous limit state function, or limit state function which is differentiable. So, the validity of the limit state function g of x less than 0 will show me that it is a failure domain through which or based on which we can extend the discussions to find out the probability of failure, as said by Elisa Falk. In 1999. Now, when we have more than one function which may be needed to define the performance of a structure, then that function is also not continuous and differentiable, then the structure must be analyzed as a system. Okay. If we have a performance function which is more than one and it is not continuous or differentiable, then the whole discussion applied to component level will get back to a system, because then the analysis should be done at the system level, as the system level should be carried out as a system. So, system reliability does not essentially mean that you are analyzing a system which is having combination of elements. It also depends upon the qualifying performance function as you see here. Hence, system can be now defined. System can be defined as we all know an assemblage of components. Each component having a limit state function, which is associated with that. Okay. And this limit state function defines the performance requirement of that component. Similar to the component level reliability problems, which considered only, let us say, two variables. What are the two variables? The safe and the failed, that is a binary variable 0 or 1. Okay. System reliability will also have two states, okay, similar to component level reliability. System level reliability will also have two states. So, let us say, for example, consider a system consisting of n components. Now, for an ith component, let us define a variable. The variable is defined as let us say can have only two states, either fail or safe. Okay. Let us call this equation number 1. This equation is valid if the ith component does not perform the intended function and has failed. The equation 1 is valid if the ith component has not performed the intended function and therefore failed. Similarly, for the entire system, we can say Z is 1 0 where 1 represents if the system is functional, and 0 represents if the system is has failed. In the whole discussion, the random variable AI is actually an indicator. This indicator specifies the performance state of the ith component. Therefore, it should be apparent for us to know that the probability A1 equal to 0 can be estimated by a component reliability analysis. Okay. So, I can write here, one can estimate, let us say A1 equal to 0 from the component level analysis, and to do this you do not require a system level analysis. Okay. Now, the indicator function AI, which specifies the performance state of the system, is actually the function of performance of its components, is it not? Therefore, AZ can be given as function of A, where A is nothing but a set of A1, A2, AN, where n is the total number of components present in the system. Let us say transpose the function, which denotes the system auction. While the performance criteria for an individual element is usually easy to determine and fix, okay, you can easily quantify this through a clearly defined simple limit state function. Performance criteria to be fixed for an entire system is generally complex. Okay. Therefore, an important step in system reliability analysis is identifying all combination of the component failure which constitutes the system failure. So, the main problem or the main difficulty in system level reliability analysis is to identify the combinations all combinations of the component failure which will constitute the system failure. Whereas, we re-insist that determining the system failure is far simple in terms of assuming a limit state function appropriately and finding out the component level failure. Whereas, a system level failure is difficult because you need to identify all possible combinations of the component failure to really declare that system has failed. Therefore, system need to be idealized. System can be idealized in two ways: series system and parallel system. A system that fails need to be identified. Let us say series system. Series system is that system that fails if any of its component fails. Such systems are often called as the weakest link systems, alternatively named as weakest link system, that is the system with weak links. We can give an example. Let us say chain is considered to be strong as the weakest link. Now, the function of the series system now can be given by let us say Az psi of A, which is minimum of A1, A2, An, which can be expressed as I equals 1 to n A. Call equation number 4. Clearly, if any one component in this system fails, which is the series system, then the product term in this equation will become 0, which amounts that if any one component fails in the system, obviously that is amounting to the system failure. Such systems are called series systems, which are otherwise called as weakest link systems. Alternatively, one can go for a parallel system. Parallel system is that system that fails only if all the components in the system fail. It is easy to now understand the difference between the parallel and series system. In series system, if any one of its components fail, system fails. In parallel system, if all the components fail, system fails. Function of the parallel system is given by Z, function of A, which is maximum of A1, A2, An, which is equal to 1 minus I call this as equation number 5. Let us schematically see how a parallel system looks like. We will draw a parallel system consisting of n components. Okay. Let us say I call this as link 1. Similarly, I can have link 2. Similarly, I can have 3, and it can continue till n. Okay. Can continue further also. This is a typical graphical representation of a parallel system with n components. One can see the equation phi, which is expressing the performance function for the parallel system of n components. It is seen that equation phi will be set to 0, will become 0 only when ai is set to 0 for I is equal to 1 to 2, 3, 4 n. That is, when all the components failed, then only the system failure will be shown. If even one component functions, then the product in the term of equation phi will be equal to 0 and the system function will become unity. Okay. It has not failed. So, it is a binary value 0 or 1. 0 means fail, 1 is functional. Now, one can also look at alternatively k out of n systems This is another way of looking at it. What does it mean? When k of the n components given in a system or of a system functions, if k of the n components of the system functions, then it is called as k out of n system. Function for the system or the expression for the performance function of the system is given by A equals 1 if go to k, otherwise 0. So, let us talk about generic form of the systems. General systems are essentially combination of the above. Therefore, a general system is a combination of the above. A general system is said to have failed if a force or a deformation can be transmitted from one end of the system to the other. Now, to analyze the general systems, it is useful to introduce the concepts of cut sets and path sets. Let us typically draw a general system which is a combination of series and parallel system. So, I have links here, I call this as 1, I have links here, I call this as 4, I have links here, I call this as 2, 3, 4. So, the system can expand either ways. So, it is a combination of series and parallel systems. With reference to this, let us try to understand what is a cut set. Because to understand the failure of a general system, we need to analyze the system in such a manner that if the force or the deformation is able to pass through the system from one end to another end, the system, the general system is appeared to be or said to be failed. To understand this analysis in detail, we have got to subdivide the general system for our understanding sake into cut sets and path sets. So, what is a cut set? A cut set is a system of components is any system of components whose joint failure constitutes a failure of the system. Let us take this example and try to mark out the cut sets for the system. The cut sets therefore are let us say C1, cut set 1 can be 1, 2, 3 and 4. Cut set C2 is let us say 1, 2 and 4. Cut set C3 can be 1, 3 and 4. Cut set C4 can be 2, 3 and 4. Cut set C5 can be simply 1 and 4. These are nothing but the paths which enables the transformation of the force or the deformation from one end to another end of the system. Okay. Now, when we talk about the failure, we already know for a component failure, for a system failure which is series, if any one component fails, system is failed. For a system in parallel, when all components fail, then the system fails. One is a minimizing function, other is a maximizing function. So, I should be able to identify now a minimum cut set from this set of C1 to C5. So, now we are talking about a minimum cut set. Minimum cut set is that cut set which is upon removal of each of its components please understand only one at a time can be removed. Ceases to be a cut set. Therefore, referring this to the figure on the board here, the minimum cut sets could be C4 and C5. These are the minimum cut sets. So, cut sets is that one, minimum cut set is that which upon removal of any one of its components or each one of the component one at a time will cease to become a cut set. Okay. So, C4 and C5. For example, let us look at C4. If we remove 4, it will not be able to connect the members, is it not? You can see here C1 has got 1, 4 connecting these two ends. C2 has got 1, 4 connecting these two ends in addition to 2, that is different. C3 has got 1, 3 and 4 connecting these two ends. C4 has got 2, 3 and 4 at least one member connecting two ends. C5 of course has got 1 and 4 connecting two ends. So, if any one component is removed, it will not be a cut set. For example, if I remove 4, it will not be a cut set. If I remove 4, it will not be a cut set. Okay? Ceases off to be a cut set. That is what we call as minimum cut set. So, C4 and C5 from this list are the minimum cut sets. Let us look at C1 for argument. So, let us say observe C1. C1 is not a minimum cut set because if you remove the component 1, still you can see here 2 2, 3 and 4 will connect these ends. So, 4 is present. Of course, if you remove 4, then it is a problem, because of course it can be still okay, because 1 will connect these two and 2 and 3 further will connect these two. So, there is a connectivity between this end and this end. Okay. So, C1 cannot be a minimum cut set. Okay. Similarly, let us observe C2. If you observe C2, on removal of component 2 from C2 or 3 from C3, do not cause either of the sets to actually cease to be a cut set, is it not? So, let us then define what is disjoint cut sets. Disjoint cut sets are those cut sets which do not contain common components. Let us refer this to this example again. These are the cut sets we have, C1 to C5. For this example, there are no disjoint cut sets, because each cut set contains component 4, is it not? All of them contain component 4. Disjoint sets are those which do not contain a common component, whereas C1, C2, C3, C4, C5, all of them have 4, is it not? So, I do not have a disjoint set in this example. Okay. That is about the cut sets, which is required to analyze or understand the analysis of system reliability for a general system. The next is going to be the path set. Path set is an alternative to this cut set. Path set is one which is any set of components whose joint survival constitutes survival of the system. Let us take the same example again here. Let us write down the path sets. P1, let us say, is going to be 4, that is this connection. There is one path. P2 came with the other path, which is 1, 2, which is going to connect 1, 2. P3 can be another path which connects 1 and 3. P4 can be another path which connects 1 and 4, which constitutes 1 and 4. P5 can be another path which constitutes 2 and 4. P6 can constitute 3 and 4. P7 can constitute 1, 2 and 3. P8 can constitute 1, 3 and 4. P9 can constitute 1, 2 and 4. P10 can constitute 2, 3 and 4. P11 can constitute 1, 2, 3, 4. So, what is a path set? Path set is any set of components whose joint constitutes survival of the system. Let us take for example 4, P1. P1 is having link 4, which constitutes survival of the whole system. Look at P2, 1 and 2, 1 and 2 connected. Look at P3, 1, 2 and 3 connected, maybe redundancy, but disconnected. P4, 1 and 2. okay. 1 and 4, let us say P4 is 1 and 4, P5 is 2 and 4. So, you can easily see this. Now, again let us talk about a minimum path set. Why we are bothered about minimum path set? Because you know the system comprises both series and parallel. Series is one which any one component fails, system fails. Parallel is one with when all components fail, system fails. So, one should identify the minimum series path, minimum path set for cut sets and minimum path set for general systems. Okay. So, let us say a minimum path set. Minimum path set is a path set that upon removal of each of its components. Of course, one at a time. Ceases to be a path set. Let us look at this list of path sets available on the screen now or on the blackboard. The minimum path set in this case are going to be, if we remove 4, system cannot exist. Okay. So, P1. If you remove either one of them in P2, let us say I remove 1 or 2, it cannot connect. So, P2. If you look at P3, if you remove 1, it cannot connect. So, P3. Okay. So, minimum path sets are going to be P1, P2 and P3. Okay. Let us look at P4. If you remove 1, does not matter because 4 is connecting. Look at P5, if you remove 2 from P5, still 4 is existing, so connected. If you look at P6, 3 and 4, if you remove 3, 4 is still connected. If you look at P7, 1, 2 and 3, so if you remove 3, 1 and 2 are connected. If you remove 2, 1 and 3 are connected, so no problem. Look at P8, 1, 3 and 4, if you remove 3, 1 and 4 are there connected. P9, 1, 2 and 4. So, remove 1, still 4 is connected, remove 4, still 1 and 2 are connected and so on. P10, 2, 3 and 4. So, if you remove either 2 or 3, 4 will be connected. P11, of course, 1, 2, 3, 4 is the maximum number of components, so no issue on it. Okay. So, one can easily diagnose the set of path sets what you have prepared for a given system and try to find out what would be the minimum path sets and what would be the minimum cut sets. Okay. Let us look at the disjoint path. Disjoint path sets are those which do not contain common components. So, for this set one can write out P1 and P2. Okay. So, friends, we are continuing the discussion on system reliability. We are identifying the series and parallel system. We are also identifying the combination of series and parallel system. To understand the analysis of series and parallel system in particular or general system, to be very specific, one should be able to understand the analysis through some definitions like cut sets and path sets for a given general system, which is a combination of series and parallel system as you see in the blackboard here. We have extended discussion to really understand or list out the cut sets and path sets from a general system. From the identified cut sets and path sets, we identified also the disjoint sets and the minimum sets for both cut sets and path sets as we now discussed. We will continue the discussion in the next lecture to really understand how the system functions for general systems can be extended more in detail to really find out the failure or probability failure of the general system based on the discussions what we have so far. Thank you very much.